Welcome back to our adventures into sequences and series. Today we're going to look at a specific type called arithmetic sequences and series. Now the key with arithmetic is that we're looking at adding the same number over and over again to get new results. In fact, if we want to define an arithmetic sequence, we can say that, or we could also call it an arithmetic progression. It's a sequence, so you already know what those are from previous adventures into this. In this particular kind of sequence, though, it's in which each term after the first differs from the preceding term by a fixed constant. Which is called the common difference. For example, let's say you have a sequence of odd natural numbers. 1, 3, 5, 7, 9. That sequence is arithmetic. If you look between two consecutive numbers in that sequence, they differ by the same value of 2. So that's the common difference. Like if you can take 3 minus 1, you get 2. Take 5 minus 3, you get 2. 7 minus 5, you get 2. 9 minus 7, you get 2. So it's an arithmetic sequence, or arithmetic progression of the numbers, and the common difference is that fixed constant of 2. If you want to do a generic, mathematical way of talking about this, you could say that in an arithmetic sequence, you can take some term a sub n and add in that common difference, and that's going to get you the next term up, a sub n plus 1. So like in this case, like if a sub n is 1, you can add 2 and you get 3, the next term. Or if a sub n is 5, you could add 2 and get 7, the next term. You can also rearrange that a little bit with a little bit of algebra. You can say that the common difference, d, is a sub n plus 1 minus a sub n. So in other words, you have 2 consecutive terms. You can take the one appearing later, subtract the one appearing sooner, and that'll come out to the common difference. So it's not necessarily larger minus smaller. It's as you're looking at the progression, the one on the right minus the one on the left when you're looking at 2 consecutive ones. And n could be every positive integer of the sequence. So you notice we like to use the lowercase n quite a bit. Another example, let's say you have the sequence 20, 13, 6, -1, -8. This is an example of an arithmetic sequence. And in order to find the common difference, you can take any 2 consecutive terms, take the one on the right, subtract with the one on the left, and that'll get you your common difference, which in this case is -7. You'll find that we like to use lowercase d to mean common difference. I mean, if you took -8 minus -1, you would still get -7. So any two consecutive terms, the right minus the left, give you that common difference. Now you can use that knowledge also to generate the sequence. Let's say you know the first term is -14. And you know the common difference is 6. Well, if the first term is -14, that means a sub 1 is -14. If the common difference is 6, then you can also think about that as adding that common difference to get the next term in the sequence. So add 6 to get a sub 2. You can say -14 plus 6, which will give you -8. For a sub 3, you can take -8, add 6, you get -2. A sub 4, you take -2, add 6, you get 4. A sub 5, you take 4, add 6, you get 10. So for that sequence, you've got -14, -8, -2, 4, and 10. Those are the first 5 terms of that arithmetic sequence. And keep in mind, your common difference can be negative too. If you're, let's say a sub 1 equals 1.5. And let's say your common difference equals -0.5. Well, you'd start with 1.5. And then when you add -0.5, you get 1.0. Then add -0.5 again, and you get 0.5. Add -0.5 again, you get 0. Add -0.5, you get -0.5. And there would be your first 5 terms of that sequence. So there you have it. As you're doing this, you might have spotted a pattern too. Like you've got a sub 1, you know what that is. You know, we found a sub 2, we took a sub 1 and added that common difference. We found a sub 3, we took a sub 2 and added that common difference. But notice that a sub 2 is the same thing as a sub 1 plus the difference. So you got a sub 1 plus the difference again. So for each new term, you're adding that difference again. So a sub 4, you could say a sub 3 plus the difference. Or you could say a sub 1 plus 2d plus the difference. So that's a sub 1 plus 3d, etc. So then you could generalize this and say, well, a sub n is going to be a sub 1 plus some number times that difference. But notice what's happening with the number. Like this 2 in front of d is 1 less than this subscript 3. This 3 down here in front of d is 1 less than the subscript 4. There's technically a 1 in front of this d, that's 1 less than the subscript 2. So we could say n minus 1 is being multiplied by d. And that gives us a nice little formula to figure out a sub n. So keep this formula in mind. It's going to be useful as you work. So a sub 1 is the first term, common difference d, a sub n is the nth term. Okay. Let's say we have the sequence 23, 20, 17, 14, etc. It's an infinite sequence because it has the ... It keeps going in that pattern. And they want us to determine a sub 16 and a sub n. Well, we need the common difference, but that's not too hard to find. We can find the common difference by taking it's an arithmetic sequence, so we could take any two consecutive terms, and we can subtract the right one minus the left one and figure out what the arithmetic difference is. So in this case, it's -3. We know a sub 1 because they already gave it to us. We know that's 23. So if we want a sub n, we can say, well, that's 23 plus n minus 1 times -3. -3 being d. You should make d a little bigger there, so you know it's not an a. And then you can clean that up a little bit. You can distribute the -3, so you have -3n and plus 3. So you end up with a sub n equals 26 minus 3n. So there's a nice little formula, basically, to find any term in that sequence. So going back to finding a sub 16, it's a matter of doing 26 minus 3 times 16. So 26 minus 48, which gives you -22. So that's one way to handle it. Let's see, another example. Let's say that the sequence has a sub 4 equals 18 and a sub 5 equals 22. And we need to determine a sub n and a sub 10. Okay, so they were nice and gave us two consecutive terms. So the common difference can be found by taking 22 minus 18. Fifth term minus the fourth term, and that gives us 4. So then we got to think for a second about, well, what would be a sub 1? Because we need a sub 1 in order to find a sub n, don't we? Let's remember that formula. A sub n equals a sub 1 plus n minus 1 times d. So let's find a sub 1. Well, if there's a common difference of 4, then that means going backwards. If you know a sub 4 is 18, then you know a sub 3 has to be 14, a sub 2 has to be 10, a sub 1 has to be 6. You just keep subtracting 4. Or you could think, well, if I'm at a sub 4 and need to get to a sub 1, then I need to go 3 steps back, and I have to decrease by 4 each time. So 3 times 4 is 12, 18 minus 12 is 6. That'd be another way to think about it. So now we got our a sub 1. We got our a sub 1 is 6. So we're going to use our formula. A sub n equals a sub 1 plus n minus 1 times d. So a sub n equals 6 plus n minus 1 times 4. So clean that up a little bit. Distribute the 4. Combine like terms. And there we go. A sub n equals 2 plus 4n, or you can say 4n plus 2, whichever one you're more comfortable with. And then finding a sub 10, it's a matter of doing 2 plus 4 times 10. So 2 plus 40, so we get 42. So there it is. Okay, another example. We have a sub 6 equals 9. We're still dealing with arithmetic sequences here. Just kind of a given. A sub 15 equals -36. We want to determine a sub 1. Well, finding the common difference here is slightly trickier because they did not give us consecutive terms. They gave us the 6th term and the 15th term. But let's go, but keep in mind, you know, like it's going to be some multiple of that common difference. So let's subtract still negative 36 minus 9, which gives us negative 45. And then let's think about how many times that common difference would have to be applied to get from a sub 6 to a sub 15, from the 6th term to the 15th term. That common difference would have to be applied 9 times, because you'd have to go from 6 to 7, 7 to 8, 8 to 9, 9 to 10, 10 to 11, 11 to 12, 12 to 13, 13 to 14, 14 to 15. Or you could say 15 minus 6 is 9. So you do negative 45 divided by 9, you get negative 5. There's your common difference. And then now to find a sub 1, think about, well, if you know a sub 6 is 9, and now you know the common difference is negative 5, then you're kind of going backwards. Instead of adding negative 5 to go to the right, you're going to subtract negative 5 or add 5 to go to the left to get to a sub 1. To go from a sub 1 to between a sub 1 and a sub 6, that's 5 jumps or 5 applications of it. So you can think about 9 plus negative 5 times 5. So 9 minus 25. 9, or sorry. Remember, I just thought about you have to subtract and add at the same time, so you're adding. 9 plus 25, which is 34. Because normally you'd be adding negative 5 going from left to right, but now since you're going from right to left, you're subtracting negative 5. So you're basically adding 5. So negative 5 times. So 5 times 5 is 25, plus that 9 gives you 34. So there it is. Now, kind of a slightly weird example is, what if you see the arithmetic sequence as a graph? So what if they graph the dots like this? Okay, so you know the domain 1, 2, 3, 4, 5, but in our range, let me plot the dots and show you where this stands. So the first one's here, second one's here, third one's here. So I should have used graph paper, I apologize, but I'll let you know where it's supposed to be. So this first dot gives us a sub 1, the second dot gives us a sub 2, third dot gives us a sub 3, a sub 4, a sub 5. So those subscripts are the domain, the 1, 2, 3, 4, 5. The actual terms have to do with this range. So I'm going to draw little dotted lines to show you what they should match up with, because my drawing's so terrible. So you end up with your sequence being 1, 3, 5, 7, 9. So there's your sequence. Now it might ask a question like, what is a sub n? You know, do a little formula. Well, we can see from this the common difference is 2. Because like if you do 3 minus 1, you get 2. Or if you do 5 minus 3, you get 2. Or 7 minus 5, or 9 minus 7. So we have a common difference of 2. So that gives us a good start. And we know a sub 1 is 1. So we could say, well, we can use our formula. Remember that? We're just doing that. A sub n equals a sub 1 plus n minus 1 times d. So we got 1 plus n minus 1 times 2. So 1 plus 2n minus 2, so 2n minus 1. So a sub n equals 2n minus 1. So now you've got a little formula. And essentially that little formula can help you to find the odd number. Notice that that's odd, positive, odd natural numbers. So now you can find any positive, odd natural number in any term. Like if you wanted to find the 10th positive odd natural number or the 100th positive odd natural number, now you've got a little formula that'll let you do it. Makes things a little easier. You might also see a question that asks about domain and range. Okay, these are individual points. So you can use the little set braces and say, well, the domain includes 1, 2, 3, 4, 5. That's those little subscripts in your a sub 1, a sub 2, a sub 3. Then the range is those y values, or the actual values you write down when you start writing the sequence. So the 1, 3, 5, 7, and 9. Okay. How about we now shift gears and talk about the series version of this? Because just like before, we have both sequences and series to think about. So let's think about arithmetic series next. And it'll be really helpful to develop some formulas to use once again. Your book does this. I'm going to just kind of do it pretty quickly. I'll just do this like in a little quick nutshell. If you're wanting to find the series, then you're taking the arithmetic sequence and adding up those terms. So an arithmetic series is the sum of the terms, just like before. You find the terms in the sequence and then add them up. So it's the sum of the terms of an arithmetic sequence. So specifically of an arithmetic sequence here. Okay, so earlier we had our sequence 1, 3, 5, 7, 9. So if we wanted the sum, you could probably just see like a capital S. So if we wanted the sum of that, you would add those up. 1 plus 3 plus 5 plus 7 plus 9. You get 25. Now, in general, S sub n, you're taking a sub 1 plus a sub 2. But remember that a sub 2 is the same thing as a sub 1 plus that common difference. Then you're adding a sub 3, but remember that's the same thing as a sub 1 plus twice the common difference. And so forth, until you get all the way down to your last term, a sub 1 plus n minus 1 times d. That lovely formula that we've been working with. So for your nth term. But then you can take that same series and you can write it a little differently. You can write it backwards. Reverse order. Begin with a sub n. So instead of writing it as a sub 1 plus n minus 1d, we'll just write a sub n. Then to go backwards, we could take a sub n minus d. Remember, going backwards, going to the right, you're adding your common difference. Going to the left, you subtract it. So we could continue in that kind of form until we get down to a sub n minus n minus 1 times d. If we add these together, we get 2 S sub n on the left. And then on the right, like you look at a sub 1 plus, you got a sub 1 plus a sub n. Add these together, again, you get a sub 1 plus a sub n. Add these together, you get a sub 1 plus a sub n. All the way down to here, you again get a sub 1 plus a sub n. Because notice that like you've got a plus d and a minus d that basically cancel out. You got a plus 2d and a minus 2d. You'd have a plus 3d and a minus 3d. Each time you add those terms, that second part goes to 0, and you're just left with a sub 1 plus a sub n. And you end up with n of these. The number n, whatever the number n is, you end up with n of these. So you could say n times a sub 1 plus a sub n. So you clean that up a little, divide by 2, both sides, and here you go. So you have a nice little formula now for an arithmetic series. In the previous video, I had mentioned Carl Friedrich Gauss. He was the precocious, very bright young math student who could add the numbers 1 to 100 very quickly in his head. Much to the frustration of his teacher, he was not kept occupied very long. So I don't know what she ended up doing to get him occupied again. But remember, his little trick was to take the numbers and pair them up. Take all 100 numbers and pair them up. Each pair adds up to 101. And you realize quickly that there's 50 pairs, because there's 100 numbers, but cut that in half, and you have 50 pairs. So you have 50 times 101, which is 50/50, 5,050. But that's essentially the formula that I have circled at the top of the screen right now. The 100 over 2, so n is 100, so you're doing the sum. You're doing the sum of the sequence of positive integers, 1 to 100, the first 100 positive integers. You're doing the sequence of that. You're doing the sum of the sequence. You're doing the series. So you have 100 of those numbers over 2. That gives you the 50 pairs. And if you add the first and the last terms together, a sub 1 is 1 and a sub 100 is 100. That gets you the 101. So it's the same thing. Same idea. Just now we have a generic formula, so we can apply it to any kind of sequence when we want to find the sum. Now you can also play around with that formula a little bit. Back to generic S sub n. All right, you've got the n over 2. You've got the a sub 1. But remember, you can rewrite a sub n. Remember, a sub n is the same thing as a sub 1 plus n minus 1 times d. So you could end up with S sub n equals n over 2 times 2a sub 1 plus n minus 1 times d. Should probably use a bracket around that since there's a little parenthesis inside. So that's another form of the formula. Because what if you don't know the last term? Like the other formula requires you to know the last term. What if you don't know a sub n? You just know a sub 1. As long as you know the common difference, you're good, and you can use this formula instead. So, gives you some options, depending on what your information is. Okay, let's do some examples with numbers, because that's the best way to really get this in our heads. Okay. Let's say you have the arithmetic sequence 48, 44, 40, 36, etc. And you need to evaluate S sub 21. So you need to find that sum, basically, of the first 21 terms in this sequence. That sounds like a lot of work. But we know A sub 1 in this case. We know it's 48. We can also find the common difference very quickly. We can take 44 minus 48 and get negative 4. So we know those two pieces of information. So that lets us use this handy formula. S sub n, I use fancy S's so you know it's an S, not a 5. S sub n equals n over 2 times A. Wait, we don't want to use the A. Yeah, we don't want to do that one. We want to do the 2A sub 1 plus n minus 1 times d. So I need a little bracket there. We don't want to use the one that's A sub 1 plus A sub n because we don't know the last term. You could sit there and keep adding negative 4 and get the 21st term, but who wants to do that? Such a waste of time. Instead, we can use this version of the formula. And we can say, well, if we're doing S sub 21, n is 21, so it's 21 over 2. And then we know A sub 1, so 2 times 48 plus, okay, 21 minus 1. And then we know the common difference is negative 4. So we can work with that. So we've got, I know I put a lot of this in the calculator when I was doing it. So you got what, 96? Then 20 times negative 4 is negative 80. So 21 over 2 times 16. So you get 168. So much faster than sitting there and trying to come up with all 21 terms in the sequence and then adding them up. I mean, you could do it that way. You could sit there and go, well, 48, 44, 40, 36, and then keep subtracting 4, or adding negative 4, whatever. Get 32, 28, 24. And you could do that all the way out to the 21st term. Then go back and add up all 21 of those numbers. And you get this result. You'd get 168. I mean, if you don't believe me, have fun and try it. But it'd be a waste of time. Oh, here's another one. This is like in the same idea as Friedrich Gauss. Sum of the first 200 positive integers. Well, that one, we know it goes 1, 2, 3, ... all the way out to 198, 199, 200. And we're trying to find the sum of this, sum of these first 200 positive integers. If you think about it, we know A sub 1 and we know A sub 200. So we can use that we can use that formula, the S sub n equals n over 2 times A sub 1 plus A sub n. We can use that idea here. 200 over 2, which is 100, so 100 pairs, times 1 plus 200. So 100 times 201, and that gives us 20,100. So very quickly, we just figured out the sum of the first 200 positive integers. And we didn't have to sit there and add them in our calculators or on our fingers. We didn't have to do 1 plus 2 plus 3 plus 4 plus 5 all the way to plus 199 plus 200. Nope. We have a formula. I like that. Let's see. Another one. Sum of the first... gives us that the sum of the first 15 terms of an arithmetic sequence is 345. So they give us that. They give us the sum of the first 15 terms is 345. They also give us that a sub 15 is 65. So the 15th term is 65. And then they want us to find a sub 1 and d. Interesting. Okay. Well, let's think about what formulas we have and all that stuff. We know a sub 15, which is the a sub n. We need to find a sub 1. Okay. So we can use that formula. S sub n equals n over 2 times a sub 1 plus a sub n. Because we're trying to find a sub 1. So we know that we've got 345. We know the sum. We know we're dealing with 15 terms, so 15 over 2 times a sub 1 plus, and then the 15th term is 65. So we're dealing. So we just solved that for a sub 1. Little algebra there. I think I went ahead and multiplied by 2 over 15 and got 46 equals a sub 1 plus 65. Then subtracted 65 from both sides and got a sub 1 equals negative 19. So there's that. And then, you know, for the common difference, I was like, I took a sub 15 minus a sub 1. And then I divided by 14. Because 15 minus 1 is 14. So 65 minus negative 19. And I divided by 14. So 84 divided by 14, which is 6. So that wasn't too bad. Last couple of examples, they throw that summation notation at us again. But it's, you know, you're adding up stuff. Little Greek sigma means we're adding up stuff. We got I equals 5 to 12 of 5i minus 10. So what it's asking us to do basically is plug in 5, get a number. Plug in 6, get a number. Plug in 7, get a number. Go all the way up to 12, get a number. And then add up those results. So you could sit and do that, but it's not necessary. Because you could figure, like when I equals 5, you can say, well, that's 5 times 5 minus 10. So 25 minus 10, which is 15. And you could consider that as your a sub 1. You can also think about I being 12. You can say, well, 5 times 12 minus 10. So 60 minus 10 is 50. You could think about that as being your a sub 12, as your, not your a sub 1, your a sub 8. Because a sub 1 is 5, a sub 2 is 6, a sub 3 is 7, etc. So 5, 6, 7, 8, 9, 10, 11, 12. It would be your 8th term when you plug in the 12. So to find your common difference, you can subtract a sub 8 and a sub 1 and divide by 7. So 50 minus 15 over 7. So 35 over 7 is 5. So we now have a sub 1 is 15, a sub 8 is 50, common difference is 5. And we're all set to use our summation formula. So summation of these 8 terms, we have 8 over 2, and it would be 8 times 15 plus 50. So 4 times 65. So that'll give us 260. Let's do another one of those with the summations. K equals 5 to 10. So Greek sigma, K equals 5 to 10, 8 minus 2K. So when K equals 5, that's going to give us our A sub 1. So 8 minus 2 times 5. So 8 minus 10, which is negative 2. So A sub 1 is negative 2. And when K is 10, so we're looking at those extremes. 8 minus 2 times 10, so 8 minus 20, which is negative 12. So going from K equals 5 to K equals 10, that last term would be our A sub 6. 5 is first, 6 is second, 7 is third, 8, 9, 10. So that's the sixth one. So A sub 6 is negative 12. We want to find our common difference. We can do A sub 6 minus A sub 1 over 6 minus 1, or 5. So negative 12 minus negative 2 over 5. Negative 10 over 5 is negative 2. And now we're all set for our summation formula. So summing up these 6 terms from A sub 1 to A sub 6, you'd have 6 over, n is 6, so 6 over 2, and then you could take negative 2 plus negative 12. So 3 times negative 14, which gives you negative 42. And there you have it. Okay, so that's everything you need to know about arithmetic sequences and series. Definitely want to do some practicing because there's some formulas there that might feel new. But if you can think quite a bit about how those formulas came about, that'll be easier than trying to just point blank memorize them. If you think about how they came about, that'll help a lot. And then just applying those same formulas over and over again, going from sequences to series. This is all for arithmetic. We still have to discuss geometric sequences and series. Now, since arithmetic adds the same number over and over again, geometric's different. You're going to be multiplying the same number. But I don't want to say too much because I don't want to, do any spoilers. No spoilers. So when we get there, you'll see. But geometric sequences can be more fun, a little more involved, because when you start multiplying, it can get a little more involved. But I'm sure you guys will be fine. All right, so I'll see you soon. Thank you for joining me.